Thank you for having me. My name is David Krakowski. I'm a research staff member over at AI Research, IBM AI Research up in Yorktown Heights in New York. I work in the Trusted AI group, and I'll be talking a little bit about some of the research efforts that we have going on at IBM Research around Trusted AI. Before I start, can I just get a show of hands of how many of you are actually involved in developing AI applications of one sort or another? Okay, about half of you it looks like. So I'll be touching a little bit on things that you might be interested in. I'll be touching on some things that are a little bit more generalized. What I'm hoping you get out of this talk is a sense of some of the trust issues that come up from AI applications that you may not be thinking of. And as I go through a few different examples, both recent and maybe not so recent, about times when trust failed and became a kind of a public PR disaster, hopefully you'll get a sense of some of the challenges that people have with trusted AI and some of the solutions that IBM Research and others are trying to work on to go ahead and address some of these concerns. All right, so let's get started. So these three quotes here and this not so quote on the bottom right is really just trying to make one point, and I think it's the point that you guys are all more than aware of, and that's that the AI is basically exploding. It's being incorporated into every domain. It's being expected to be incorporated into every business, right? And this should be of no surprise. I'm sure you're more than aware of the fact that AI has just been being embraced left and right by every industry. On the bottom right is a little factoid I want you to put in your pocket. We'll come back to it later. Basically, what it's trying to tell you is this notion that if you're an AI developer or a knowledge worker, as we sometimes call them, the majority of work, according to the research that you do, is not actually developing AI models and improving AI systems. It's actually the dirty work, collecting the data, cleaning it up, making it useful to be incorporated and used by AI systems. So just put that little factoid in your pocket. We'll come back to it later. At IBM, of course, we are doing exactly what those quotes are saying. We're applying AI to a number of different domains. I put up 8 examples here just to kind of give you a scope of different things that we're doing. On the compliance front, we're scanning regulatory documents and laws as they come in an effort to go ahead and see whether your company is compliant with new regulations as they come in. Similarly, in the media world, we're going ahead and identifying strategic initiatives from various articles in news and other publications. On the customer care side, and perhaps more interesting to this group, we've developed chatbots to help people determine what is the right insurance policy for them and their particular needs. On the healthcare side, we're trying to help doctors identify breast cancer more accurately than they do just by hand. In the media world, we're doing instant replay automatically, even generating commentary for it. We have people in the lab actually working on drones to visually inspect utility poles and try to identify rust and other maintenance issues. In the IoT space, we're working closely with farmers in the Midwest to go ahead and identify, through a combination of aerial photographs and sensors on the ground, crop yields. So how much crop can you expect to have given the current census data that we have? And finally, in industry, we're helping people, helping industrial professionals troubleshoot the problems that they have with their components. So really the takeaway from this slide is there's a lot of different domains that AI applies to. We're working in a lot of different ones, and there's a lot of excitement about the applicability. It's really one of these technologies that, as those quotes seem to suggest, is really ready to impact a number of different domains, a number of different businesses, a number of different companies, and really change the way that we think about things. But of course, with that come a lot of different issues, and we'll get to those in a moment. So unsurprisingly, a huge technology like this is really going to come down to doing 3 things, and I'm not going to spend a lot of time on this slide, but it's either going to increase the value of your business, it's going to decrease the cost of doing business, or it's going to enable you to do something new and different that hasn't been done before. So this should be nothing new. You should be all familiar with this. Okay, before we get into the trusted AI bit, I think I need to establish some groundwork. So you often hear these terms: artificial intelligence, machine learning, deep learning. How are they related to each other? I just want to make sure that everyone kind of knows the terms that I'll be using, just so we're all on the same page. So artificial intelligence, you can basically think of any system that's trying to think like a human. It doesn't necessarily have to be like a human, but it's very open-ended. It could be a rules-based system, it could be a statistical-based system. It's basically some program or system that's trying to make a decision for you. And then within that space, a subset of that is machine learning. And the way that machine learning differs from general artificial intelligence is the system is using some kind of data to go ahead and learn, usually through correlations or other statistical means, some information about that data such that it can reason about it. Most often in classification. Of course, the canonical example is like a Netflix recommender or Amazon recommender, right? Takes on the information of what you've watched and what other people similar to you have watched and give you a recommendation. Same thing with Amazon, right? You get a whole bunch of information coming in about what people purchased. They purchase something that you purchased, well, you might like the same thing, right? So there's not really a lot of intelligence there. It's really just fancy statistics, but it is what it is. The big one, and the one that's really kind of changing the impact and really driving those quotes that I showed on the first slide, is deep learning. And deep learning, again, is a subset of machine learning. It's, again, a statistical model, but it's one that's tied to a particular representation of knowledge called a neural network. And I'll go into a little bit of AI 101 and walk you through what a neural network looks like. It'll be at a high level. Hopefully it won't be too scary, but with a little bit of luck, we can get through it without too much issue, and you can kind of understand why some of these issues around trust and other things are starting to emerge. It's really a consequence of using this particular type of machine learning. Hopefully that's clear.
Can you give an example of AI that is not machine learning?
Sure. Any rules-based system. So if you have you used if this, then that?
Oh, yeah.
Yeah, that's AI. That's a rules-based system.
Okay.
Yeah. In that case, it's very explicitly coded, right? But the idea is to go ahead and have the machine make a decision for you based on some constraints, right? When you program the constraints, it's different than if you just extract it from the data you're given. Any other questions? All right, let's move on. Okay, so AI 101. So here is a very complicated picture of a neural net, but I promise it's not as complicated as it looks. So what I want you to see is here on the far left, we have 5 nodes in vertical column. Those are your input nodes. On the far right, you have your output nodes. And in the middle, each column represents what's called a different hidden layer. And the way you want to think about this is as we go ahead and train a neural network. Let's say, for example, that I'm trying to train a classifier for images. So I have an image of a horse, and I want my neural network to tell me, hey, that's an image of a horse. So to go ahead and train this system, I would take the horse, I would put in the inputs. The inputs would latch on to various features of the image, maybe a specific pixel or a group of pixels or some other feature about the image, and then propagate information, usually through a nonlinear function, about that image to the next layer, which would then forward propagate it to the next layer, which would then forward propagate it to the next layer. And then through these series of propagation, which you can just think of weights being pushed through a graph, you end up with a final set of weights, one for each possible prediction. Whichever one is the highest is the one that gets predicted. So in this case, the highest one was monkey, which unfortunately was incorrect. So what do you do when it's wrong? Well, you back propagate. So you take the error that you found from being monkey. In this case, you know which nodes in the graph contributed to the prediction of monkey. You know that's wrong. So when you back propagate, you go ahead and adjust the weights such that it's no longer giving that much weight for that particular image to monkey. You do this thousands and thousands and thousands of times, and over time, the network averages out such that it picks up on, oh, this kind of cluster of pixels happens to be a horse. This kind of cluster of pixels happens to be a monkey. And that information is encoded in these hidden layers. And what's really, really, really troublesome about neural networks and deep learning in particular is these hidden layers, these 3 columns in the middle, which could be way more than 3, is not something that maps very cleanly to what humans understand. It's not like saying that this node identifies that this type of nose is a horse's nose. It's nothing like that. It's very much taking the information from the image, often just the pixel data, or maybe differences in values or some other transformations might happen in an image, and trying to make sense of it in a way that humans don't comprehend. So we have this gap. We have the gap between what people think about when it comes to classifying that image as a horse versus what a machine's thinking about when it classifies an image as a horse. So really high level description. Hopefully that didn't confuse anyone too much. But my goal is to give you a sense that, you know, it's a little complicated and it doesn't map very cleanly to how humans reason about things, and that's where a lot of the problems come into play. All right, so we've entered an era of what I like to call a deep learning explosion. And I've touched a little bit onto why one of those 3 points, algorithms, has contributed to it. Really, with advancements in deep learning algorithms, especially over the last decade or so, we've really opened up the possibility of solving all sorts of different problems that were considered intractable before. Things like speech to text, image recognition, computer vision, identifying breast cancer cells, etc. The other two big changes that happened recently are on the compute and data side. On the compute side, it's very straightforward. GPUs continue to get faster, they're highly parallel, they're really open now and easy to program against, and you can do a lot of the type of matrix math and vector math that you need to do a neural network that you weren't able to do 10, 20 years ago. So it's just the power of computation. The last piece, and I really love these three statistics here, is the data side. You need a ton of data to do this well, right? You need a lot of training examples to do these types of things well. And nowadays, we're just ingesting data at a ridiculous rate. Give you a couple examples. YouTube, they get 400 hours of video uploaded a minute. Walmart handles 2.5 petabytes of customer data per hour. That is insane. That is a tremendous amount of data. Facebook has 350 million images uploaded daily. And I know those statistics are outdated. Those are at least a year old, so I'm sure they're all much bigger than they are now. The other interesting thing is because you have the right amount of data and because you have the right algorithms and because you have the compute power that you need, you're now entering the point where for some specific tasks, the machines are doing it better than humans. So if you remember from food you're eating, you're going to find a nutritional label on it, right? And that's nice, detailed, it's partitioned, it's very standardized, it's very regimented. There's a required minimum set of information and some optional information that a company can choose to include. Like if they want to highlight that your cereal isn't just sugar, but in fact has those 10 essential minerals and vitamins, you want to know that it's there. And then kind of on the other spectrum, kind of more of a binary approach, you have something like the Energy Star label, right? It meets some minimum requirement for energy usage. So the point here is that there's a number of different standards bodies that already exist, and we're not necessarily promoting a standards body, but we're taking the idea of, hey, can we do something like a nutritional fact label for models or AI services? And so we actually wrote a paper about this very topic. It's on arXiv. There's a link to it right there on the bottom if you're interested by reading it. This one's done from the perspective of what can I report about a service that contains AI that I've deployed? And we've called that fact sheets. So what type of information can you expect to find in a fact sheet, the kind of nutritional label that you find for a model? Well, here's a few different examples. I'm not going to read them all. I'm just going to wait a few seconds and let you read through a few of them and get a sense of what type of information might be conveyed and might be useful for a consumer of a given AI service. Oops. Okay. So you have a fact sheet. It has some facts about the model, let's say. Some of these facts might be generated automatically as you're developing your model in scikit-learn or Jupyter Notebook or whatever the case may be. Some of the information, if you recall from the back, was actually something that might have to be written by a human, right? And so there's this kind of combination of factual data for a model, and there's this information that's handwritten and specifically handwritten for a specific purpose. And really, that's kind of what I think is the main conceit of a fact sheet, is this idea that you customize the needs of the fact sheet to whatever use case you have. So for example, if you're creating a fact sheet for your development team, you probably don't need to go into specifics of regulatory bodies. You don't need to go into specifics of release information. You don't need to go into specifics on what data set necessarily this was trained on. You're on the development team, you probably know these things. You maybe just care about the basics of the model. Tell me how it performed so I have a history of all the different models that we tried. Whereas if I'm creating a fact sheet for a regulator because I'm a financial institution like Chase or JP Morgan, and I have a regulatory body coming in and asking me, guarantee me that the models you're using are not biased, right? The types of information that I might want to include on a fact sheet are very different. Right? So the idea behind fact sheets is you have this kind of customizable, configurable thing that can be output in a variety of different formats based on the needs of the particular use case. So the idea isn't really all that new. There's, this has been done in other domains. There's some other work in academia, which I can point you to if you're interested in this type of work. But the gist of it is, if we can centralize all the information that data scientists and all the information that data scientists need when they're building models, because it tends to be scattered across a number of different tools. It tends to be scattered across a different number of platforms. It tends to be scattered in folders in Excel spreadsheets somewhere because they had a local instance running, right? What if we can just kind of pull all that stuff together and actually give it a cohesive field that has historical data, has provenance, and is able to actually tell you something about the history of how models developed in a standardized way. So that's the main conceit of fact sheets. I'm going to skip past these two slides. And I think the only other point really to make about fact sheets is I think the level of detail and the level of regulation in fact sheets is going to really depend on the types of industries involved. So if you're creating a model with some friends on GitHub, you're probably just doing like a bare minimum set. Like, tell me the performance characteristics of the model you just built, and we'll compare it with the one that I built, and we'll see which one's better. Whereas if you're, again, like a large financial institution that has a lot of government regulation, or an insurance body, again, with a lot of government regulation, you might have an authority come down and say, this is what a fact sheet should have, right? Or maybe there's certain laws that you definitely want to capture while you're developing the model. So that's basically the idea of fact sheets. Okay, I'm going to pause again. Questions? Okay, let's continue.
You kind of touched on this a little bit. You mentioned sometimes a regulatory body goes into what should be on a fact sheet. Is there any sort of other research, or like what is the bar in the case where there's not a very clear regulatory body on how does something make it into a fact sheet?
Yeah, so again, I think it's very use case specific. So I can envision instances where there might be a role that's job is like, here's the information that we absolutely need to know at every step of model development. So someone might pre-develop a list of items that need to be in a fact sheet, and those would then get propagated throughout the team and filled out as the development was going on. Whereas in some cases, it might just make sense to have a really simple, sensible default. Like, here's just the basic information. Here's the input that was used to train the model. Here's the training performance characteristics. Here's the model performance characteristics. That's what you get for free, right? Or maybe not for free, but with a little bit of effort. Any other questions? All right. So this is the last part of my talk. I promise you all can go home soon. So I'm going to talk a little bit about not necessarily what offerings we have, Watson Studio and Watson OpenScale regarding AI, but talk about how the challenges that are maybe unique to this space, right? How does this space differ from traditional software engineering, and what are some of the other things that you might have to think about if you're developing AI or applications that contain AI? So we'll go through this relatively quickly. So what is an AI lifecycle? I talked about lifecycle management. It's very similar to a software engineering lifecycle, except now you also have this model component to it. And this is just the model component. So if you've ever designed a model, this should look very familiar to you. You have some data preparation, you have some modeling, and if you're lucky, you'll have a chance to iterate and update that model. Unlike traditional software systems, there's some quirks, some nuances with AI, right? In a traditional software engineering environment, you might create some unit tests, and every time you run that unit test, you're going to get the same result. In an AI world, that might not be true, right? The model might be different, might have been updated. With each update, it could spit out completely different predictions. It could get better, it could get worse. So there's this danger that a small change can go ahead and completely change the output of your model. There's also exactly what I touched on a moment ago about competing metrics, right? Sometimes you want to push accuracy and you want to push performance, or you have a constraint that your model has to run on a smartphone, right? And you want to consider these things when you're developing your model, which may not be equivalent to the types of constraints you're dealing with when you're dealing with software engineering. And what's particularly interesting about this is it's very data and analytics driven. While you're developing models and you're iterating and you're improving models, you're deploying models, you're pulling in real-time data and updating models, that's all going to be data-driven. You're going to run the types of evaluations to convince yourself that every update of your model that you do is ticking up whatever metrics you care about in the right direction. Right? And this is very different from software engineering. We're often not doing any kind of performance level type of testing, in most cases, on software. All right, it's mostly just debugging, and debugging a model is a whole other story. All right. On the managing risk side, what's interesting here is the way that the current software engineering and model engineering lifecycle goes. These are often two very just separate processes, right? The people who are your data science team will be working on creating a model, and they're not concerned with integrating that model into your application, right? So they kind of have their own lifecycle, and the software team has their own lifecycle, but there's this very strong dependence between the two, right? So there are questions about, are there things we can do to bring these two life cycles together? Can we encode these dependencies in a way that's meaningful? Are there other ways that we can mitigate risk? And most commonly, this is done through guardrails. At least this is what we've observed. So this is things like, don't allow a model to give a prediction when certain conditions are met. So for example, you may not want to use a model to give a credit score prediction if the person is under 18, for example, right? Lastly, or not lastly, but also deployment differs from traditional software, right? The definition of better in an AI model is hard to pin down, right? Better might be less accurate, but faster. Better might be unbiased, but less accurate, right? So what's better? It's going to depend on the use case and depend on kind of the constraints of whatever environment you're working in. Furthermore, in AI models, you often ensemble models, right? You take a whole bunch of models and you glue them together to come up with a different result. And when you do that, how do you actually reason about that? Do you want to reason about each individual model? Do you want to reason about the models as a whole? How do you actually expose that information and document it? And finally, there's this monitoring piece, right? Models, unfortunately, are very, very sensitive in most cases to drift. So if the input that you trained your model on is very different than the input that your model sees when it's deployed, it's not going to perform as you expect. Or maybe it is the same when you started, but over time, your audience changes. And now you're getting different inputs, and so your model's not performing as well. Well, you have to keep track of that. You have to notice when it happens, and you have to do something about it. The thing about traditional software is like I feed it the same inputs every time. I'm always going to get the same outputs. That's not true in this world, especially if you're updating your models. And then finally, what's particularly interesting is when you want to improve a model, the single best way to do it is with new data. And anytime you add new data to a model, it could potentially upend everything. So how can you be intelligent about which data you're using to fix your model? Are you doing your statistical tests to verify that your distribution of your input data that you're using is actually what you're seeing in the real world? Are you doing that extra effort, right? Do you have the statistician telling you like, yeah, you got to be careful about these things? Because if you don't, they can have a real widespread impact. And then finally, it's just very similar to DevOps. You got to iterate rapidly, you got to fail fast. You'd like to know your model's not doing what it's supposed to do as soon as possible. So these are just some of the differences between model development and software engineering that make any kind of platform that supports model development a little bit more complicated than maybe what we're used to. All right, so let's wrap it up. So some conclusions. Fairness and explainability can be limiting factors in AI adoption. It may be difficult to use a model if it hasn't been debiased, for example. What else do I say? I didn't talk about robustness, but the point being made in that second bullet is you want to think about more than just the accuracy of your models when you're creating them, right? And we're hoping to help provide tools to address some of the other issues that you may not be thinking about. And I'm hoping here at the end of this talk, you're now thinking about things like trust and explainability and robustness and how you actually assess models over time. And I think I'm just going to conclude there.